cooling pads, it's good to put some time in and make sure everything's right, because these pads are the heart and key that actually make the air get cooler. Now there's quite the debate over which is better, synthetic or natural. These are wooden aspen fibers. As for how often to change them, some folks do it several times in a season, while others will use the same ones all year. I suppose a lot of it depends on if your water is hard and makes a lot of deposits.
Or there could be a concern about a buildup of mold. It's alive! It's alive!
I personally keep the same pads for the whole season, but I change the water every few weeks, wiping down and rinsing the inside of the cooler cabinet several times before refilling.
Rinsing and cleaning can go much quicker by temporarily removing this drain tower.
Mine unscrews without a wrench. Now after cleaning and filling with new water, I always add a couple tablespoons of laundry bleach, and that helps keep the mold from growing. I do this because my water comes from a private well and it has not been chlorinated like it is from most city and town municipal water supplies. Now where I live, there's a problem with every wasp, hornet, and bee finding its way inside looking for moisture. So I not only change the pads, I add this non-metallic heavy-duty window screen, cut it out and put it in there first, and that really helps keep the critters from getting inside. I make sure and cut it big enough so it'll wrap around all the edges, and I cut little slit openings so the screen will lay down flat over these handholds, fitting the screen down each one so it lays flat. They'll try and get in anywhere that you don't cover up, including the drain on the bottom of the cooler. I had a whole little hornet's nest up inside of there once, so I installed this aluminum window screen to protect the hole. Here's how my aspen pads came from the store. It took 3 and they're about $5 a piece, and there's where they're bragging that they're better than paper or synthetic. They come in several standard sizes, but none of them were small enough for my little cabinet, so I'm going to have to cut them to fit. Notice how the whole piece is wrapped and surrounded by this netting to keep the fibers contained. So when I cut this to fit, if I don't do something about the edges, it's going to fray out like this and clog up the works. So the first thing to fit this is to put a factory edge down along the bottom and along this side, but it thins out, so leave a bit extra there. And on this top, I'm going to make a cut up to this piece here. So I mark a black line, and I want another cut there.
To cut this material, I'm going to use some garden trimming shears.
To get this new cut edge to have the netting over it, a neighbor taught me this neat little trick. There's the line we need to cut, so I'll make another mark about 1.5 inches further away and cut it there. So here's neighbor Tom's excellent idea. I lay a straight edge on the line that we really want and proceed to pluck out the fibers while holding down the straight edge. Then I'll take the extra netting and fold it under on the line that we want, and that gives us a protected netted edge. To cut this top edge, it's similar, but I have to first cut the netting open with some scissors. Then I plucked the fibers out back to the black line I marked. Then, like I did before, I took the extra netting and tucked it underneath. Now for this edge, I want to fold the netting that's already there a little bit further in than the very edge because it got thin there. So now here's my custom cut pad ready to install. I want to make sure the pad's really tucked into these side rails and that it's pulled all the way down to the bottom. Remember how I cut those screens to fit over these handholds? Well, I'm going to cut through the netting and into the fibers a little bit so that this pad will also lay down flat over those handholds. Now it's time to reinstall these pad retaining grills. Here's how it should look from the outside with the critter blocking screening in place, including the two handholds. Now if I hold this pad up to the sunlight, you can see that there are places where the fibers are thinner and thicker. And I don't think it cools as well where it's thin. Well, if I wanted this pad to work at its very best, I could carefully make a slit opening in the netting over the thin areas, tear apart another new pad, and use its stuffing to fill in the thin place through the slits in the netting, adding some of the fiberglass window screening to cover over the slits in the netting. Fans for 24 volts. Well, there's three different ways to approach this. The first is to use two 12-volt fans connected together in series as shown here. One's negative goes to one's positive, and then you end up with the two wires there. And that's shown here in the schematic at the end of part 4. But the drawback of this way is that the fans are kind of like Siamese twins, where they have to get their power through each other. So if one of them changes, wears down sooner, it's going to cause some problems. But with new fans and some good luck, I've seen this way run successfully for 3 years straight. The second method is obviously to just use 24-volt fans. They're harder to find than 12-volt, but I've seen some out there like Spall, and I don't know anything about them, but they are a little bit pricey, but supposed to be good quality. And they can be ordered in either the pusher or the puller versions. The third and final method is to use a 12-volt fan. Say I found a great big beautiful one like this, but I couldn't run it in my 24-volt system. Wrong. Everything in the system would support it just fine. The only problem is if you turn up the speed switch over halfway, that fan's going to really take off. The fan could be OD'd on that. So I'd need to put some kind of stop in the speed control switch so it couldn't go past halfway. A screw or a dowel.
On 24 volts, that fan would be full blast.
Some of these generic universal car radiator fans come configured to be pullers, sucking air in, or pushers, blowing air out. Some of them can be changed to be the other way by changing which wire goes to positive and which goes to negative, which will reverse the motor's direction, and then taking off the fan blade and flipping it over. With some fans this doesn't work. See this little spacer under here? That helps keep the fan away from rubbing onto the grill. So if the fan rubs when it's flipped over, sometimes making this spacer thicker can help. But if nothing seems to help, then the fan probably can't be converted. If I thought I bought a puller but I got a pusher instead, I could just mount it the other way around in the cabinet and use it that way. Now here I am flipping it over, making sure the flats line up. Put the washer and the nut back on and secure it good and tight. Now if I ever get confused as to which way the batteries connect and which way this is supposed to turn, I'll just temporarily hook it up to a battery and feel the wind blowing. If it isn't a whole lot of air blowing, then maybe I've got it hooked up backwards, or the blades are on backwards from what I thought. Some of these fans come with balancing weights on their blades. An unbalanced blade will cause the whole unit to vibrate at higher speeds and cause the bearings to wear out prematurely. If this fan felt smooth and balanced before I flipped the blade over, but then felt rough and vibrating afterwards, I would remove the fan, rotate it half a turn until the clip ended up over here, then reinstall the fan and see if that helps. And when I'm testing these fans out loose on the ground, I always wear these welding gloves so I don't chop my fingertips off. Actually, even these gloves might not be enough to prevent injury. Best to just keep my hands away from the spinning blades. Bare hands and spinning blades is a disaster waiting to happen. So is my design for a pusher or a puller? Do I have a pusher or a puller? Gotta know before I start building the design. Most original equipment car fans are suction pullers. This test meter is a real handy item to have when doing this low voltage DC wiring. They measure volts, ohms, and some of them even measure amps, and they can help you figure out which wire you're measuring, if it's positive or negative, and if power is even present, and many other helpful things. I'm sure there's some good YouTube videos that show how to use them. I got this one on eBay for less than $50, and they go on up past several hundred. This is the rheostat that adjusts the water output of the pump. It's shown here on the schematic drawing, inserted in the positive power wire to the pump. The main reason for having this is to match the water output of the original pump, about 5 or 6 liters per minute, where my pump puts out 10. I figured out how much water the original pump put out by having it fill a known size bucket and timing it for a minute, setting up my test bucket to be high enough to match the lift, the height the pump experiences when it's working in the cooler. Then I did the same test again with the new pump and temporarily wired in this rheostat and turned it till I got approximately the same amount of water output, making sure to later mark the rheostat with a black marker to show where it was positioned. This rheostat can get hot to the touch on the green part during use. When mounting this rheostat into the bracket, this little tab has to have another hole drilled for it. I first drilled this one, but then I changed my mind and drilled this one to make the rheostat wires be in a better position. There's the little tab. Now I'm going to use these 2 connectors on this rheostat. This third one is not used, so wiring it that way will make it, when I turn the rheostat clockwise, I get more water. To know where this rheostat is turned in its circle, I put reference marks on the shaft and by the tab. Now here's two different brands of the rheostat I found on eBay, and they're slightly different in the way that wires can be connected to them. For the center post, I found it easier just to solder the wire to it, but for this one, the metal on the side terminal is a kind that can't be soldered to, so I ended up using that screw-on terminal. But if I was going to end up using this one, its side terminal is a metal that you can solder to, but I had to first clean out some green ceramic that spilled into the hole from the manufacturing, and then bend the terminal up like this one, and I also tested it to see if solder would stick to it, and it did. When soldering these terminals, the idea is to keep the solder from puddling out onto the ring. So first off, I want to approach the piece with my solder not on this side, but on the back side there. Then I want to heat the gun up first, dab a little solder on, set it down on there and get the piece hot and feed a little solder in. But I've already made two mistakes. One, I put too much solder on the tip and I fed too much solder in. I also stayed on there too long, should have got on and off quicker. Now here I'll just exaggerate it and show what happens. You end up with this big puddle lump out on the ring, and that's going to prevent a good full electrical contact of the screw. The same issue also applies to the larger terminals when I'm using the torch for heat. But if this happens, I could either chop the thing off and put another one on, try it again, or I could heat it up real hot, dump off the extra, and then use a wire brush to clean it off while it's still hot. It doesn't have to be totally smooth, it just has to be not lumpy. And the backside usually has to be brushed off too. I wanted to mention a few things about wiring up this disconnect box. There's small wires into big lugs and big stiff wires. So this cooler power cord wire is very small gauge in a big lug. So what I do is strip it off twice as long as it needs to be and fold it over so it's doubled up. It's also been coated with that antioxidant paste because this is an outside environment. Now with these big stiff number 8 wires, there's another problem, and that's that when you think you've tightened them down, they're not really tight. They have to be wiggled, tightened some more, wiggled some more, tightened some more, wiggled some more, and then they're tight. Loose wires make a bad electrical connection and over time can heat up, ruin the box, even cause a fire. I also wanted to mention that on this power cord wire to the cooler I added some split flex tubing. Also important, this green ground wire coming from the cooler should go all the way back to the earth ground of my power system and connect to the earth ground circuit there. This wire can be one size smaller than the red and black power wires. This fan speed control switch is okay, but it's pretty light duty build, so I want to replace it with a heavier duty version. They're easy to find on eBay, etc., about 10 bucks. So what I need to do, obviously, is transfer the wires over to the new unit. It's just a mimicking of the way they are on the original one. I want to make sure I write down where each one goes so I don't mix them up. Then I'm going to cut off the 2 wires that go to the back side, and with these 2 it doesn't matter if I mix them up. Right now, while these wire ends are loose, it's a good time to slide on this rubber grommet. Remember in part 4 we were talking about this. So now's the time to slide one on over these 5 wires before I start soldering. Next I'm going to take the first 3 wires I cut off and strip the insulation off the ends of them. Cut off 3 pieces of heat shrink tubing, load them on, then run it through the correct hole, twist it around, connecting it to the new unit. Then I repeat the process with the other 2 wires. Now it's ready to solder. Then I slide the 3 heat shrink tubings down and shrink them. Then I proceed with the same process for the 2 wires that go on the back side. When mounting this rheostat in the box, this little tab has to go through one of these 2 holes on either side of the center. See, there's the tab right there. When I put this nut back on, I do use a wrench, but I'm not showing it here. And now I can use the stock factory knob. This cooler wiring might look intimidating overall, but if I just take the wires one at a time, it's really pretty simple. And success is more likely if I double check my work, even triple check. So starting with the fan wires in the lower left corner, I'm using twist-on connectors, and the 2 wires come on up here and connect to the control box terminals for the motor. And here's the original factory power cord bringing the DC in. There's positive to here. And here's the DC power negative coming in right next to the positive. And the green ground wire just hooks there to that metal screw. Now from these same power terminals, I'm going to be taking wires off. There's a positive going through our little fuse for the pump, and it just dead ends right there for now. Then from the negative terminal, a wire comes off and goes down, 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 through the grommet and down to the pump and the float switch. Then another wire comes off the negative, coming down to a female disconnect. All of these wires eventually hook to the front control panel, and this one is to the pump on light from the rheostat. This one's to the low water warning light, and this one is from number 30 and 86 on the relay to the on-off switch. Now here's where the relay is located generally, but it'll be tucked back under the box for some of these views. So with that in mind, this blue wire comes from the float switch connecting to the wire from number 85 on the relay. On the schematic you can see there's the float switch and the wires coming up to 85 on the relay. And in the real world, on the bottom of the relay you can see the numbers. I'll make these tape labels for each wire so I can keep things straight and not mix them up. Alright, so the red wire comes out of the grommet from the pump and comes up here to the center tab, which I soldered. And this other tab goes to number 87A on the relay and out to the front pump on light. Here's the pump on light, the pump switch, and the low water light. This was already mentioned briefly in part 4, but I wanted to talk a little bit more about these resistors in the 2 light circuits. They're cheap and easy to find on eBay, etc., but they have to be bought in a bundle. Can't get 1 or 2 at a time. Now on the schematic, here's the pump on light and the low water light. And you see there's the resistor for that one and the resistor for that one. And they both come together on a common negative. But notice in these pictures that I didn't hook the resistors here. I hooked them on the positive side, on the red wires to these lights. And that left these 2 negative legs just simply to hook together and go back. It made wiring simpler. So you see that's why this resistor is hooked to the positive red wire on the LED lights and not the negative. Now with these 2 LED lights, the red wires must go to the positive. The negative wire on one is black and the other is yellow. So for the negative leg, the 2 wires are spliced together there and continue on to a male disconnect. The positives of each light have the resistors in them and they continue on. The blue is the pump on light and the red is the low water light. Now for the pump on off switch, these last 2 red wires come off the switch and it doesn't matter which goes where. And they're just raw end terminals for twist-on connectors. Now to connect these wires up to the rest of the system. The common negative black wire from the two LED lights goes up here and hooks onto the negative that we'd left dangling there before. The blue positive wire from the pump on light connects there and goes up to the rheostat side terminal. The red positive wire from the low water light comes and connects there and travels up back in there to number 87 on the relay. Now for the pump switch wires, one of them goes up to the orange wire from the little fuse and a twist-on connector. The other one goes over and twists on to the white wire, which goes back to number 30 and 86 on the relay. Now this is the same unit just a few minutes later after I folded or coiled the excess wire back underneath the switch box. The one thing that's new is that the power cord is now positioned in its little slot on the front cover. Now if my cooler keeps going into the low water pump shutdown when it really isn't low on water, especially when I first turn it on, I can go in there and bend this metal bracket down and put the float switch in a better angle. That should help. I don't want to overdo it, a little at a time.
I feel good right now.